let me get a few more people in the chat screen up. Okay. Oop, that's my office hours thing. Let's get to the right page. Okay. Hi, so good to see you guys. I got to see Delaney's face for a second. That was nice. Good to see Joby. That makes me smile. So, hi, Delaney. Okay, so let's see. So I'm about a little more than half finished with the exam. I'm going to commit to getting it done by tomorrow at noon. I know that's pretty late, but you still have all the information from the other thing that I posted on the Google Drive if you want to make decisions on pass-fail before then. So those are my hopes and dreams, and I'm just going to stay up tonight until it happens. And does anybody have any questions before I start talking about math?
Do we have until midnight tomorrow to choose if we want to go pass-fail, or is there like a certain time?
That's a good question. I don't know, but we were sent, you might have been as well, we were sent a list of pass-fail FAQs. Did you get that message?
I don't remember getting it, but I'll check.
Okay, Nick just wrote 5 p.m.
Yeah,
so,
I saw that. Okay.
Yeah, so maybe that's believable. That seems more likely actually than midnight. Okay, thanks for adding that, Nick. Okay, so let's see, we were talking about curl and divergence last time, so that's section 13.5. And let me let in Adrian. And we had just started on a new idea, and Delaney had explained very well how this certain idea was true, but I just want to put it up again because it's going to lead into what we're talking about today, part of what we're talking about today, and that's when we're talking about curl of conservative vector fields. And so Delaney made the point that if we had a vector field that had any curl at all in it, so so maybe the vector field had some little patch where the vectors were kind of rotating around, then we could exploit that by choosing a curve to integrate around. We could choose this as our curve C, and then the line integral around that C would not be 0, so that would say not conservative. So, so in other words, what we just discussed was curl F not 0 means F not conservative. Or the other way to say it, the theorem is that if F is conservative, then the only way that can happen is if curl is 0. So then here's my question. Does this give you a way to prove that F is conservative?
Yes.
Would it be no?
No, yeah, can you explain why?
Well, I just kind of know from my discrete mathematics class, like how conditional statements work.
Yeah.
So like, you can't, like, it's just, I don't know how to explain it, but just like the way it's worded, like even if it doesn't have any rotation, it could still be conservative. I don't know if that's explained right. I mean, wait, no, I said that.
You have the right idea about the implications. So the idea is that, so we have a statement that says something like, if P is true, then Q is true. But P is a hypothesis. It doesn't say anything about P being in the conclusion. So you're right, that's the structure of an if-then statement. What I'd be asking you would be the converse of that, and that's not necessarily true. So I'm going to say, this statement itself, not necessarily true, so not necessarily. In fact, it doesn't give us a way to show that, so I'm just going to say no. And it's the same that we had for theorem 6. Remember that for theorem 6, we had a statement that if the vector field was conservative, then those cross partials would be equal, right? Q sub x would be equal to P sub y. And then did it go the other way? Well, if P sub x equals Q sub y, did that mean F was conservative? Do you remember that theorem?
No.
No, it didn't mean that, but we had to have extra conditions. So if we had that, plus there was a simply connected region over which the cross partials existed and were continuous, then that was enough. So we had to have that tiny little piece more information. So that's going to be the same thing here in this case. So, so no, but it does give you a way to show. But it does give a way to show F not conservative. Okay, just to finish that old comment, and that's right here. If the curl is not 0, then you can show F is not conservative. But if you have a little bit more information, then it is enough to show that it's conservative. So, but it statement is true if you have a little more information. Statement in the question is true if we have a little more information. Okay, so what would that more information be? Is a theorem, and it's called the curl test. Okay, so suppose, here's some conditions. So suppose, so first of all, the curl of F is 0. And F and all partials are continuous everywhere. Then that's enough. Do you see how this is like theorem 6? Theorem 6 said if the cross partials are equal, if Q sub x equals P sub y, and all the partials are continuous on some simply connected region, then that's what you need to get conservative. We have the same thing here. They've relaxed it a little, or they've tightened up a little bit to say everywhere, because they didn't really want to talk about what does simply connected mean in 3 dimensions. That's too complicated. So this isn't the most general possible statement they could have made, but this is a true statement. So so that's good. Okay, so maybe you don't remember because I didn't rewrite it, but maybe I should have. So remember that the curl looked something like, I'm gonna get it wrong because I usually work it out every time, but let me try to figure it out. It's gonna be, so if F had components P, Q, and R, then this is going to be probably something like Q sub Z minus R sub Y. Oh, I don't really remember. Let me add in jack. And then probably R sub X minus P sub Z, and then Q sub X minus P sub Y. Is something like this. I don't know if I would totally take my word for it. So let me just say it's approximately that. The reason I'm saying that is because I'm trying to point out the connections between theorem 6 and the curl test. Theorem 6 was 1 dimension down, but just cared about this thing right here. And that's the thing that we deal with when we talk about the curl of 2-dimensional vector space. Remember, this was the scalar curl that came out of it. So the curl test really is just a generalization of that theorem 6 up to 3 dimensions.
Dr. Hoffus, I think you switched the first 2 components of curl.
Did I? Which ones did I get backwards, Colin?
I think it's RY minus QZ, PZ minus RX, and then the last one is right.
Oh, these are both backwards? Okay, thank you for correcting me. So ry minus qz. Oops. And then this is pz minus rx. Okay. Okay, thanks for correcting me. I knew there were some parts like that, but I also thought I might get it wrong. Okay, and still this piece right here, this piece is related, is the part that comes from theorem 6, and it's also our version of the curl when we're down in 2 dimensions. So this is just a generalization. Not a generalization, just a version of theorem 6 for 3D vector spaces, vector fields. Okay, so when I say all partials, how many partials do I mean here? How many partials are there? If f is like this, so f has 3 variables and 3 component functions, how many partials are we talking about?
9.
9, that's right, because it's going to be, it's going to be p sub x, y, z, q sub x, q sub y, q sub z, r sub x, r sub y, r sub z, so 9 of them. So that's just all 9 partials. Okay, so, you know, that's a lot, but the ones we're dealing with, generally that's going to be true, and it's going to be easy enough to check. Okay, so, and if any one partial is not defined somewhere, it's inconclusive. We don't really know. But this curl test will give us some good information. Okay, so sort of building on this, what about, think about curl of a gradient. So what if I have a real valued function, little f? So 3 input variables and 1 output variable. Then what is the curl of the gradient of f?
0.
Yeah, that's exactly right. Why is that?
Because if it has that's a conservative function or a conservative vector field since there's a potential function.
Exactly right. Yeah. So this is just building on this theorem right here, which says, oh wait. Yeah, which says if it's conservative, then the curl is 0. Well, look at this. This is the most obvious version of a conservative vector field. It's obvious because it's already expressed as the gradient of a potential function. Okay, so, but let's think about what this means in terms of this little f. Rather than curl of big F, think about what it means in terms of little f. So what it means is, so if I have so let's think of some sort of reasoning, so the idea behind this. If I have a graph of a function, which I'm going to have to draw down here. If I have the graph of a function, remember how we have these functions. I can only do this in 2D because I'm drawing it in 3D. I don't have enough components for it. But let's just sort of think of the idea. Ooh, am I going to be able to do that? Yeah, I'm not going to be able to make an analogy in 2D. So we'll just have to talk about the ideas. So if I have a 3D function, we know that it's a real value function. So that means at every point in the room, there's a number associated with it, which is the output of that function. And at some points in the room, we're going to have higher values, and some points in the room, we're going to have lower values. But we know for sure that the gradient vector field, if we take the gradient at every single point, the gradients point in the direction of, what do gradients point in the direction of?
Greatest possible change.
Greatest increase of the function. That's right. And so the gradients are going to kind of be going, go this way to get bigger, right? And then so in some sense, they're kind of pointing at the best way to get to a maximum. How do you get off of your current value and towards higher values as quickly as possible? And so this is just sort of a heuristic, but what if there was some curl in that? Then what that would mean, it would be something like, so if a gradient vector field had curl, that would mean that there would be some place that did like something like this. So it would be kind of like, you know that Escher picture where there's like, it's like a castle, and the top of the castle there's these stairs, and people keep going up the stairs all the way around, but then it's sort of an optical illusion. Has anybody seen that picture? Yeah, Joe has anyways? Okay, that'd be kind of what's going on here, right? Because think about this, if this were the gradient vector field, then the gradient would say, hey, go this way to get bigger values, go this way to get bigger values, go this way to get bigger values, go this way. You couldn't keep going around in circles towards bigger values. It wouldn't work. So if gradient f had some curl, then it would send you in circles while directing you towards larger values, which just isn't possible. Okay, so that doesn't happen. Okay, so that's the end of what I wanted to say about curl and divergence, but of course we're going to be using that pretty regularly for the rest of the semester, so I'm happy to answer questions right now if anybody has one.
I have a question. It might be completely invalid just because I haven't learned about sequences since my senior year of high school, but does the divergent in this have any relationship to like when you're trying to find if sequences converge or diverge?
Oh, it doesn't have a relationship mathematically, but it does in the sense that diverging, as an English word, means sort of spreading apart, and converging means coming together. So when you're thinking about sequences in series, diverging means you're not coming together, and converging means just going towards some limit. And then that same thing's happening with vector fields. So the concept of diverging, that sense means the same thing, but I don't know of a mathematical connection between the ideas. But that's clever, actually. I hadn't even thought about the fact that it was the same word. So yeah, but I don't know any mathematical connection between them. Anyone else have a question? All right, cool. So that's curl and divergence, and we'll see those again. We'll see those again in 13.8 and 13.9, and maybe before. You'll see them again tonight for homework. All right, 13.6. Here we go. Parametric surfaces and their areas. Parametric surfaces. Okay, so we're going to do something completely parallel to what we did for line integrals. So just to give you an overview, remember what we did for line integrals. So first thing we did a long time ago, like one of the first days of classes, was we figured out how to parameterize curves. And then we talked about two versions of line integrals. One was line integral of a real valued function, and one was line integral of a vector field. And we talked about what both of those meant. And then we figured out ways to calculate them. And then we figured out, we learned there were some theorems that could make calculating them easier. You could use the fundamental theorem of line integrals, which is like the fundamental theorem of calculus, and that would sort of give you, you have to just plug into a potential function. Or in some cases, you could use Green's theorem and swap a line integral for a double integral. Sometimes a double integral is easier. Okay, so that's the summary of what happened in 13.1 through 13.4. Now let's talk about what's going to happen 13.6 through 13.9. It's the same, it's a parallel story. So the first piece of the story is, how do we parameterize these things? How do we parameterize surfaces? Then this little piece about their areas, well, I guess I forgot to mention that part of the story for one dimension. We did parameterizing curves and their lengths. Remember the very first thing you did was arc length of a long time ago? So now we're going to do parametrizing surfaces and their areas. Not because areas is the most important thing, but because it's a nice warm-up for thinking about surface integrals. Then we're going to talk about two types of surface integrals. One's going to be integrating a real valued function over a surface, and one's going to be integrating a vector field over a surface. We'll talk about what both of those things mean. Then we'll have some theorems that will relate some of the computations, make some, replace one integral for another integral, maybe make some computations easier, that sort of thing. So let me just say, here's a outline for the rest of the semester. So first, we're going to learn to parameterize surfaces. Then we're going to practice surface integrals just by finding the areas. Then we're going to learn about two types of surface integrals. And that's surface integrals of a real valued function or surface integrals of a vector field. Same way we had for line integrals. And then we're going to have some theorems which help calculate these. Which can be shortcuts of various sorts. Okay, and actually, maybe I'll just sort of add in here as a little reminder, when we did for the vector field line integral, we had to talk about orientation. We didn't care about orientation for real valued, but we cared very much about vector fields because vector fields have built within them a direction. So we had to talk about direction. Okay. So the exact same thing is going to happen here. We'll need to talk about orientation of a surface and what that means for surface integrals. Okay, so that's where we're going. And here's how we're going to get there. So remember when we were talking about when we were talking about parameterizing curves, I gave you 3 types of curves that you would need to know how to parameterize. And then I said anything else I would give you, or the book would give you the parameterization. Same is true here. So, and you know I'm serious, because remember when I said that a long time ago, how many times we've seen those 3 things to parameterize since then. So you really do need to know how to parameterize these 3 things. Well, kind of 4 things. Maybe I squished that too close. You're going to need to know how to parameterize 4 things. First of all, well, so straight things. So when we had curves, we were doing parameterizing curves, straight curves were lines. Well, straight surfaces, 2-dimensional things, are planes. So we'll have to parameterize planes. Also, for curves, we had graphs of functions. Same thing's going to be true here. What's another one we had for curves? What's the remaining one we had for curves that we had to know how to parameterize?
Did we say circles?
Yeah, circles and ellipses. And then what's the corresponding thing in 2D? I mean in 3D for surfaces.
So then spheres?
Spheres, that's right. Spheres. Usually I give an example with ellipsoids, but I think since we're in a compressed time slot, I'm not going to do that this time. But yeah, so I'll just leave that out. And then here's a 4th kind of thing, which is a little bit hard to describe, but as soon as I do one example of it, you'd be like, okay, yeah, I know what you're talking about. I'm just going to call it things with round cross sections. Okay, so let's just talk about all of these. So, or maybe I should remind you, why do we parameterize things? Well, why did we parameterize paths? Sometimes paths weren't the graphs of functions. So same thing is true. Why would we do that? So first of all, sometimes surfaces aren't the graphs of functions. For example, the sphere. But we still need to describe, instead of telling you what every single one of these infinitely many points on the sphere is, we need sort of a formula, a function that can describe how to get to every point of them. So parametrizing is the thing that can do that for us. And another thing is, this is a more esoteric thing. I think I told you when we were talking about line integrals. See, if I have a curve, I don't care if it's in 2D or if it's in 3D like this, it's a one-dimensional object. It's living in 2D, 3D, maybe 5D. Who cares where it's living? The point is, it's a one-dimensional object. And so it makes sense to describe that using one parameter, one variable. As one variable changes, you can cruise along it. So the same thing goes here. A surface is a two-dimensional object. So a sphere itself, and I'm not talking about the stuff on the inside, we're just talking about the crust of the ball, right, which the boundary is the sphere. That is two-dimensional. It has to live in 3 dimensions, but itself, it's just each little patch is like a patch of a piece of paper, not like a patch of something solid. Okay, so surfaces are two-dimensional, and it makes sense to describe them with 2 parameters. No matter if they're living in 3D or not. So it makes sense to describe with 2 parameters. Okay, so that's what we're about to do. Okay, so what is it going to look like? So the parameterization form. Well, before we had for curves, we had r of t, and we had some x value as a function of t, y value as a function of t, maybe a z value as a function of t, and then some bounds on t. That was the form of the parameterization. What's it going to look like for surfaces? Well, for surfaces, we're going to need two parameters. We're going to call them u and v. And then each of these dimensions, x, y, and z, will be just the value in each of these coordinates will be given as a function of u and v. So this will be x of u and v, y of u and v, z of u and v. And so then we're going to have bounds on u and v. So okay, so that's going to be the form for parameterizing surfaces. Okay, let's just start. So the first one that we wanted to talk about was planes. So here we are. Well, you know how to write the equation of a plane, but I'm not really talking about the equation of a plane now. I want a parametric version. You can get one easily enough if you have the equation of a plane by treating it as a graph of a function, but let's just suppose we don't. There's sort of an easier way to do it. So do you remember, I'm just going to keep doing the parallel for lines to help you understand, help you make connections with something that you already understand. So recall lines. We needed a point and a direction vector. And so we had a point P and our direction vector V, and then the parameterization was r of t. Can somebody tell me? Please tell me everybody knows this.
P plus T times V.
Yeah, P plus T times V. Okay, so we could start out at some point, and then we had some direction vector, and then any multiple of that vector is going to get us someplace on this line. Well, let's just generalize that to surfaces. So if I have planes, what we're going to need is still a point. And then, see, if I look at this picture right here, one vector only gives me one line. But if I added another vector, then I could start getting all over a plane. So maybe I can draw a convincing picture. So here we are in 3 dimensions. We have some plane that's sort of angled in some weird direction maybe. And then I've got some point on it. If I have 2 vectors, let's see. If I have 2 vectors that are parallel to the plane, yeah, I need a different color. Like here's V and here's W, let's say. Oh, V is bad since I'm using V as a parameter. Okay, let's say W and what's another good about? What's a good variable for a vector that's not U and V and W? X, Y, and Z means something. T is a parameter. I'll just call, and P means something. I'll just call it Q. I'll just call it Q. Okay. If I have these 2 vectors and a point, that's going to be enough to get me to any point on the plane. Why is that true? Well, if I start at P and I add 1 vector Q onto it, I'll get there. But if I add 2 vectors Q on it, I'll get there. If I add -1 vectors Q on it, I'll get there. So I can get anywhere along this one line on the plane. If I instead add one of the W vectors, I can get here. But what if I add 1 W vector and 1 Q vector? Then I'm going to get here. If I want to get to this point, say, I can just add half of a W vector and half of a Q vector. Does that make sense? So I can get to any point on the plane by doing some multiples of 1 vector plus some other multiples of another vector. So what do I need? I need a point and I need 2 vectors parallel to the plane. So let's call that point P and let's call the 2 vectors W and Q. Then the equation is just what you would think. Then the parameterization is R of U and V is starting point P plus any multiple of W plus any multiple of Q. So it's just like oh, I covered it up on my screen, but you can't see that. It's just like if we didn't have this part, if we only had this part, that's for a line, and then we're just sort of adding it to stretch it out in another dimension. Okay, so I think I did a poor job of explaining that. So I'd like to hear questions that could help me make it a little clearer. Does anyone have a question?
The only thing is, so the 2 vectors we have, they just can't be parallel, right?
Yeah, that's right. They can't be parallel to each other, because if they're parallel to each other, then you're only going to draw out one line. That's exactly right.
Okay.
Yeah, so maybe I'll say parallel to the plane, yet not parallel to each other. Yeah, that's a good point. Okay, any other comments? Okay, it's just a generalization of what we did for lines. So this is it for planes. And then if it's an infinite plane, then there's no bounds on U and V, but usually we're not going to be dealing with infinite planes, because if we're integrating over it, if we add up something over an infinite space, we're likely to get an infinite answer. So we're usually going to have bounds. So the bounds, just like when we had lines or line segments, the segment bounded the t values, while the size of the patch of the plane will bound the u and v values. So they'll need bounds for u and v. And we'll do some examples of that, so you'll see where that will come from. But that's the basic idea for a plane. Now, let me see what time it is. Okay, we have till, okay, good. So that's the basic idea for a plane. And maybe let's do an example. let's say I give you 3 points. Given points P equals 0, 1, 0, Q equals 4, 1, negative 1, and R equals 2, 1, 3. Write the equation of the plane through those, write the parameterization of the plane through those 2 points. Okay, so this is just going to be a representative picture. I'm not going to get P and Q and R in the right places necessarily. It's just sort of a schematic. Just so we get the ideas, we've got these points, P, Q, and R. There's P, there's Q, and there's R, say. And what do we need? We need a point, and we need 2 vectors parallel to the plane. So need yeah, the point's easy. We could either choose P or Q or R. Let's just choose P because why not? It's the first one. How am I going to get vectors parallel to the plane?
You just do like PR vectors.
Yeah, PR. We're going to just do displacement vectors. So the displacement vector from P to R and the displacement vector from P to Q, for example. We could do any of them. We could do displacement vector from R to Q or any of these things. We just need 2 of them that aren't parallel. So let's use from P to R and from P to Q. So let's find them. PR is, let's see, coordinates for R minus the coordinates for P. And PQ is coordinates for Q minus coordinates for P. Oh, that's interesting. Okay. So those are our 2 vectors. Then if I want to parameterize it, I'm just going to say R of UV is point plus U times PR plus V times PQ. Point was 0, 1, 0 plus U times 2, 0, 3 plus V times 4, 0, negative 1. And there, it's parameterized. It's usually nicer if you put it all into one, if you combine it. So the X component, I've got 0 plus U times 2 plus V times 4. X component is kind of weird. Look, the X component, I've got 1 plus U times 0 plus V times 0. So the Y component. So the Y component's always 1. And that's just an accident of how I randomly pick these things. I happened to pick it so the Y component was always 1. So okay, there it is. That's what I got. And then what's the Z component? 0 plus 3U minus V. Okay, so there's our parameterization. 2 parameters. And if I wanted to find an actual point on the plane, well, we already know P, Q, and R, but I could find another point. All I would have to do is just choose values for U and V. U equals 3, V equals negative 7. Plug it in, I've got a point on the plane. That's what it means to parameterize the plane. Any value that you plug in for the parameters will give you a point that lies on the plane. Okay, so that's what I was going to say about planes. Who wants to ask a question about that? Planes, solid. Okay, now let's talk about case number 2. So if we go back to this list where we're going to do planes, and yay, let's do a little green check. Yep. And then now graphs of functions.
I got a question.
Sure.
Usually if we're given a plane, are we also given the points so we can find the equation of
You'll
it?
be given, that's a really good question. And you'll be given planes in a variety of ways. So one thing that was really challenging about, for example, 10.5, that's when we learned about planes the first time, is that these questions could be asked a whole bunch of different ways. Like I could just say, what's the plane line that contains these two lines? And I could give you an equation of two lines. And then one thing you could do is you could find 3 points on like maybe the intersection point and then a point on each of these lines, and then that would do it. Or you could take like an intersection point, you could take any point and you already know the direction vectors for the line, so you could just use the direction vectors as your two parallel vectors to the plane. Or, you know, there's a whole bunch of different ways that you can be given that information, and you're right, it may not be given to you exactly like this. You might have to do some sleuthing to get out either two vectors parallel to the plane or 3 points in the plane. It'll depend on the context. Okay, let's talk next about graphs of functions. Okay, well, so what do I mean by that? So if I have a function like this, which is a two-variable function, and I'm letting the z value be the output of the function when I plug in x and y, well, then it's kind of already expressed in terms of two parameters. If I'm talking about this surface itself, this surface is already expressed in terms of two parameters. The x and the y value, you know, those are random. And then once you choose an x and a y value, those are, I mean, independent, then you plug that into your function, that gives you a z value. That's it. So the parameterization, just like for curves, it's just going to be r of, let's use x and y for our parameters. X is just x, y is just y. What's z? Where do we get the output from? I just gave the answer. Sorry, where do we get z from? Z is the output of the function. Okay, so this is the same thing that we did for graphs of functions in 2D, except now we've just got, you know, an extra parameter. Okay, that's all there is to do for that one. If we do an example of that, like parameterize the graph of this function. So it's just going to be the x value is x, the y value is y, but the z value comes from the function. And it's parameterized. Okay, that's the second thing. What questions do you have about that? Third thing, spheres. So I've got some sphere. If I have a sphere, let's just put it at the origin. And let's say it's got a fixed radius. Let's say it's, oops, I didn't know. Let's say the radius is 3. How could I parameterize this sphere? What parameters, what coordinates do we like to use as spheres?
Rho, theta, and phi.
Rho, theta, and phi. Excellent. That's 3 of them. And but we really only need 2 parameters. So 2 of those values change, and one of them stays fixed. Which one stays fixed?
Rho.
It's the rho. Yeah. If you have a sphere, then the radius is constant. And I mean I did write rho equals 3 right here, but in any case, that's true for any sphere, right? If you have a sphere, the radius is constant. The thing that's changing is the phi and the theta. So the phi and the theta, those are the parameters. So if I want to parameterize this sphere, I could say r phi, well, it's theta and phi is, well, what is the x component? 3 times sine phi cosine theta. the y component is 3 sine phi sine theta. Oops. And the z component is 3 cosine phi. And then if you want to do the whole sphere, you're going to bound phi and theta between 0 and 2 pi or 0 and pi. If you want to do part of a sphere, you're going to have to limit those bounds, but it depends on what the context is. Okay, so spheres, you already have natural parameters right here, and so we'll just use those. Things with round cross sections, well, really, I'm going to hold off on that until we're actually doing a problem with it. But what do I mean by things with round cross sections? Maybe we can just do one. What if I have, so what are some things with round cross sections? So those are the things that we like to use cylindrical coordinates for. Somebody tell me some shapes that are good for that. Sorry. So I'll start cylinders.
Cone.
The sort of ordinary boring type of cylinder. Cone, good. What else?
A cone.
Yep.
Oh, that's what he's.
We got that one. Anything else?
Like a spiral thing.
A spiral thing. Okay, so a spiral thing is, might be a curve and not a surface.
Okay.
And I'm not sure what you think about for a spiral thing, but when I think of a spiral thing, that's just a curve.
Just almost like a cylinder,
Paraboloid?
but like spinning around. That's what I was thinking.
Paraboloid, cylinder spinning around. So, okay, so paraboloid, absolutely. And if you're talking about, so Connor, if you're talking about something that's gonna go like this, is that the sort of thing you're thinking of, or am I misunderstanding you? Okay, well, so this would be a curve. Paraboloid, yes, also like hyperboloid of 2 sheets, hyperboloid of 1 sheet. Okay. So the idea is going to be cylindrical coordinates. Can help. Let's maybe just do, what if we do one example, the sort of easiest example to start with, like a plain old cylinder. Let's suppose it's this one. Let's not get that easy. Let's get a little weird. Let's go down the x-axis like this. And let's just say the radius of the cylinder is 2. Okay, so then how am I going to parameterize this? What are the parameters that I can use? If I want to describe a point on that surface, what information do I need to do so that I can communicate to you which point I'm thinking about? Let's see, I know if I've got the cylinder like this, I know how far I am from the origin, so I don't need the R. But what I don't know is where I am sort of around when I look down the barrel of the cylinder, and I don't know how far down the cylinder I went. So I could use a theta to talk about where I am rotated around. So maybe I'd measure theta like this. So I'm going to go on from the positive y-axis like this. And then what coordinate should I use to describe where I am up or down that cylinder? There's a natural choice for that.
X.
X, that's right. Okay, and so the X coordinate is just given by X. How do I get the Y and the Z coordinates? If I forget about X and I compress into the Y and Z, I have a circle. So how can I get the Y and the Z coordinate? How do we do a circle?
With cosine and sine.
Yeah, with cosines and sines. So this is going to be 3 cosine theta, 3 sine theta.
Why is it 3 again?
Why is it? Because it's supposed to be 2 and I just misremembered. Sorry, thank you for pointing that out. I had a 2 in here and then I kind of accidentally wrote over it and then I forgot what the number was. Yeah, so it would be 2. Okay, and let's suppose I added to this question and I didn't want the whole cylinder because the whole cylinder is infinite, but I just want the part of the cylinder that goes between, let's say this is -3, and let's say it goes all the way to here, and it just ends here at +5. Then that means X is bound between -3 and 5. What about theta?
Those all have to be like from like 0 to 2 pi, right?
0 to 2 pi, that's right. What if I was only talking about the top half of that cylinder? What would I change?
0 to pi.
Just 0 to pi, yeah, that's right, okay. So when we have things with on cross sections, lots of times we'll want to exploit the fact that we have cylindrical coordinates that we understand, and that's going to help us give a really nice parameterization. Right, there's parameterizing things. Yeah, let's use it. So let's figure out how to find areas of surfaces. So this, remember, this is our warm-up surface integrals, and it'll be fun. Okay, so area of surfaces. Okay, so well, whenever we found the length of a curve, remember we just added up little patches of little pieces of arc length until we got the whole thing together. So recall curves. So we had some wiggly curve and then we approximated it with line segments like this. And we split it up into some number of subintervals along. We got a bunch of line segments, and then we added up the lengths of the line segments, and then we took the limit as the number of little line segments went to infinity, and then that gave us the curve. But the point is that we added up small pieces of the curve of arc length. Small pieces of length of the curve to get the whole thing. Same thing's going to be true for surface area. If I want surface area, I'm going to add up small patches of surface area and then patch those surface areas all over the surface till I get the whole thing. So let's say, for example, let's think in terms of a graph of a function, because that's something that we're maybe the most used to. So we've got this function, the z value is f of some x and y value. And at any point, yeah, there's an x and y value that So x naught, y naught, let's say, that puts us right here. And at any point, there's tangent vectors. There's a tangent vector that heads in the direction of the x-axis, and a tangent vector that goes like this. And those things are going to describe a tiny little parallelogram. No, I should have done it. Let me try it. Let me do this again. The tiny little parallelogram that it's going to describe is going to be this one right here. So it's like, so I've got this curvy surface, and then at some point, there's a tangent plane. And at this point, there's a tangent vector that sort of given from the partial derivative with respect to x, and a tangent vector given for the partial derivative with respect to y. So what I've got is two tangent vectors to the surface. Those two tangent vectors lie in this tangent plane. So what we're going to do is we're going to take, the area of this tiny little patch of tangent plane, and that's going to represent a patch on the surface. Well, the patch on the surface is actually, it looks like, oh my gosh, it's underneath it, stuck to the surface. And the flat patch is probably sticking up. Here's the curvy thing, the flat patch is probably sticking up like this. But it doesn't matter, because remember, when we do infinitesimal, whenever we added all this up, these line segments were not segments, they got smaller and smaller and smaller and smaller until it actually just fell in along the curve. Same thing's going to be here. When we do this, when we integrate, these patches are actually going to be infinitesimally sized, and so they're gonna fit along the surface just fine. Okay, so we're going to have small patches of surface area, and what we really need to do is figure out how to get a little piece of surface area. So without me doing too much detail right here, what if this vector, what if we just called this vector r sub x, and this vector r sub, I want it to be there, r sub y. That's what those vectors are. How can I get the area of this parallelogram?
You take the cross product?
Yes. So close. If I take the cross product, yes, but then what do I do with the cross product? Oops. Because the cross product is a vector, so that's not 100% what I want. No, I want to move that, but I can't.
Take the magnitude.
Yes, the magnitude of the cross product. Oh, I'm so glad you guys said that. So the magnitude of the cross product vector. So the cross product vector itself is going to be a vector. What direction is it going to aim?
Perpendicular.
Yeah, perpendicular to the surface. So the cross product vector r sub x cross r sub y will be perpendicular to the surface, and the magnitude of r sub x cross r sub y is the area of that little parallelogram. So that's the thing that we're going to be adding up. Here we added up, these things were like called ds, and remember that was dx dt squared plus dy dt squared plus dz dt. And we added up those little pieces. Now what we're going to be doing instead to find the surface area is we're going to be adding up, we're going to be integrating these patches right here. And the size of one of these patches is just what we just said, which is magnitude of r sub x cross r sub y dx dy. Okay, that was in the special case where I drew it with x and y being the parameters. We usually use u and v. I'm going to use U and V when I write down the actual formula, which is here. Okay, so here are some pieces. So the surface area, well, okay, sorry. Let me get my head in the game. Okay, so if I have a parametrization of a surface, then we're going to call the surface area element which is a tiny piece of surface area. That's going to be d capital S, which is the magnitude of RU cross RV. Okay, unfortunately, d lowercase s, that's what we use when we're talking about arc length. D uppercase s is what we're talking about for a surface area element. Okay, and the reason it is that this is the tiny piece of area. Okay, actually, there's a piece that I'm really glossing over here, which is this is sort of scaling du dv over in u and v space. It gives you the area of some rectangle, and then this piece right here is scaling that up to be the area of what the parallelogram is. There's something about UV coordinates being over here and sort of mapping into it that there's some details that I'm just going to slough over. But in case you want to really get into the details and realize there's something missing, that's the thing that's missing there. Okay, so there's the surface area element, and in order to calculate the surface area, you add up all the little pieces of surface area. There's going to be the double integral because there's two parameters, and then the bounds are whatever they are. If I didn't include them in the problem, maybe I should have. Let's do that. So A less than equal to U less than equal to B, C less than equal to U less than equal to D. Then U is going to go from A to B. B is going to go from C to D. And we're just going to add up all these little pieces of arc length. Sorry, all these little pieces of surface area. And that will give us the whole area of the surface. So that's the integral of ds. Let me just keep this here since we've been talking about it. We're also going to have a need for, so I forget who pointed it out, but they were correct. The cross product vector is perpendicular. I don't know how to make it perpendicular like that. I don't know. The cross product vector is perpendicular to both of those both of those vectors, r sub x and r sub y. So it's also perpendicular to the surface. And we're going to need that information later on. So I'm just going to sort of put that here so everything's together, but we're not going to talk about it for a little bit. I'm going to call it the surface element, not the surface area element. It's not a little piece of area, it's a little piece of surface. Vector, it's a vector representing a patch of surface. Unfortunately, we write that as D capital S with the vector on it. I didn't make it up. That's just what we use. And it's not the magnitude, it's the vector itself. It's this perpendicular vector right here which is perpendicular to this surface at this point, and it has the correct magnitude. The magnitude of this is the area of that little parallelogram. So it's just RU cross RV dUdV without the magnitude. Okay. Let's try to do an integral. Well, does anyone have a question before I get into integral? I know this was a lot of abstraction and you might be at wit's end at this point.
Does the order of du dv matter?
No, good. I'm glad you asked. Not at all. It doesn't matter at all. And except that just like for any double integral, you know, if you've expressed u between the bounds for u as a function and the bounds for a v and then the bounds for v are constants, you're going to want to put the function on the inside and the constants on the outside. But other than that, it doesn't matter at all, however you want to do it. Although also we saw that sometimes for some integrands, it's easier to integrate one way or the other. So that might be a consideration, but that's not because it's incorrect to write it the other way. It just may be easier to evaluate to write the other way. Okay, I think if we do an example, it'll help bring all these abstract ideas down to something that we can really talk about. So let's try that. Let's find the surface area of the sphere of radius capital R. You might think to yourself, well, this is stupid because I already know what the answer is, but that's why I picked it, so that when we did the calculation and got the right answer, we'd have this nice warm feeling that we did it correctly. Okay, so, well, does anybody know the answer to this for surface area of a sphere? Oh, okay, maybe you don't. So some of us, when I say we know, I'll say I know that surface area will be 4 pi r squared. And let's just see if we end up with that. So, well, what are the things that we need? Well, I really want this surface area element, but the only way I can get this surface area element is to do what? What's always the first step?
A point?
Point. Okay, well, we won't want a single point because we'll have to integrate it all over the whole thing. But I guess when I did here, I did like a representative point.
Parametrize?
Yeah, parameterize. We're going to want to parameterize. And so let's do that. So first, parameterize the sphere. Okay, well, we know how to do that. So the parameters for a sphere are theta and phi, and the rho is a constant, capital R. So that's going to be the x value is capital R sine phi cosine theta. The y value is capital R sine phi sine theta. And then the z value is capital R cosine phi. And the bounds on theta are between 0 and 2 pi. And the bounds on phi are between 0 and pi. Okay, parameterized. Now, we really wish we could integrate this surface area element. So we need to figure this out. Look at all these pieces. We need R sub u, we need R sub v, we need the cross product, we need the magnitude, and then we can integrate it. Okay, so let's try to do some pieces. So I need some partials. So let's say find R sub theta and R sub phi. Those are our parameters in this example. So let's see. R sub theta. Here's the parameterization. I need to take the partial of this with respect to theta. So first component is going to be negative R sine phi sine theta. Remember, this is a constant. All this is a constant. So that just comes along for the ride. And then derivative of cosine is negative sine. And then this is going to be r sine phi cosine theta. And then this is going to be 0 because there's no thetas in the last term. And then r sub phi is, I'm going to have to speed up a little bit, I think, in order to finish this during class. R sub phi is going to be r cosine phi cosine theta, r cosine phi sine theta, and then negative r sine phi. What do I do with those two things? Look at the formula.
Cross product.
Take the cross product, absolutely. So let's find r theta cross r phi. None of these are too hard for us. It's just that there's so many steps to do. That's what feels overwhelming. So let's do that. So r theta cross r phi. Let's see, so let's see how much we have to space it out. So negative r sine phi sine theta, r sine phi cosine theta, 0, yikes, negative r sine phi sine theta, r sine phi cosine theta. We'll put this one in, r cosine phi cosine theta, r cosine phi sine theta, negative r sine phi. Okay, we need to take that huge cross product. So I'm just going to connect these like I did before. Here's what we're figuring out for the I values. And then let's do red for what we're going to figure out for the J values. And then I'll do green for what we're going to do for the K values. Okay, and we take a deep breath and we tell ourselves we're not afraid. And then we try to do this. So if I'm going to go this forward direction, I have r, this looks like a negative r squared sine squared phi cosine theta. Minus the backwards direction, oh, that's minus 0. Because look, at 0 times this, that's just going to go to 0. Okay, J value. Going forward, I get 0. Going backward, I get minus a minus a minus. So minus r squared sine squared phi sine theta. Then for the K value, going forward, I get negative r times r, so negative r squared sine phi cosine phi sine theta. And then going the backwards way, I have minus an r squared sine phi cosine phi cosine theta. That's probably horrible to watch somebody else do and trace through it. But if you go back later on and just do it yourself, you're going to get these values. Okay, so I know that you can do this computation. So let's try to simplify it a little bit. This is going to be, so I've got negative r squared sine squared phi cosine theta, negative r squared sine squared phi sine theta. What about this last term? So this last term, I can factor out an r squared sine phi cosine phi. I don't know if that helps or not. Times sine theta plus cosine theta. Now what? Magnitude.
Integrate.
We don't even get to integrate yet. Don't we wish? But we need to take the magnitude of it. We have a vector, and we need to take the magnitude to get a scalar. So here we go. Find the magnitude of r theta cross r phi. Well, it's going to be the square root of first term squared, r to the fourth, sine to the fourth phi, cosine squared theta, plus second term squared. I feel very nervous about, did I do anything wrong with the k?
Is it supposed to be minus cosine squared theta?
Yeah, that's right. That's right. Okay, so I feel much better about this. So I did make a mistake with the k values. So if I look at this again, I should have negative r squared sine phi cosine phi sine theta. I forgot the sine theta down there. I just didn't see that. So it should be a sine squared theta and a cosine squared theta. I'm so much happy about that. So then this is a sine squared and a cosine squared, and then yay, that goes away to 1. Okay, thanks for finding that for me, Dylan. Okay, so I'm less scared now. And then this is r to the fourth sine to the fourth phi sine theta. And then this is r to the fourth sine squared phi cosine squared phi. Okay. Each of them has an r to the fourth in it. I can factor that out into the front and take the square root and just get an r squared out of it. Well, let me do some grouping. So if I connect, let's see. Here I have a sine to the fourth cosine squared theta. Here I have a sine to the fourth sine squared theta. I forgot to write the squared. And so if I factor out a sine to the fourth, I'm going to have a cosine squared plus a sine squared, which is 1. Does that make sense? And then I'm going to have then I factored out the r to the fourth. So I just have a sine squared phi, cosine squared phi. Okay, so that goes away to 1. So now I have the square root of sine to the fourth phi plus sine squared phi. I can factor out a sine squared phi. Then I have a sine squared phi plus cosine squared phi. Oh, hey, that's cool. That's 1. So I've got r squared sine phi. Where have you seen that before? Do you recognize that?
Is it similar to the dv for spherical integrals?
It's exactly that. That's the sort of scaling factor we have to put in for the dv for spherical integration. This is where it comes from. This is the calculation that produces that. We just remembered it before, but now we know where it comes from. So classes, I don't have time to do this integral, but I did the hard part. So the surface area, is going to be, well, the double integral of ds, which is the double integral of r squared sine phi d theta d phi, and theta goes from 0 to 2 pi, and phi goes from 0 to pi. And this is a pretty straightforward integral now. And when you do it, you're going to get 4 pi r squared, if you do it right, beta r squared. Okay, there's a lot of steps. You know how to do all the steps. You just grind your way through it. And then hopefully you have somebody else like you guys help me out when I made all these transcription errors to fix things. Okay, you know enough to do both homework assignments. I was gonna do an extra practice problem with you. Would you like me to put 13.6 off until Wednesday after we do another practice problem? How do you feel?
Yes, please.
Yeah.
Yeah, okay, we'll do that. So then homework Tuesday is 13.5, and then Wednesday is 13.6. And maybe some more stuff. Start 13.6 now because we might finish more stuff. There's not very much to do of 13.6, then we're going to do 13.7. So yeah, start.
But you said we have enough to do 13.5 and 13.6.
Yeah,
or start
that's right. I think you can do. I mean, I've only done one example, and so you may feel comfortable with another example or two more examples. But there's no new information to give you before you can do those. Okay, happy to see everybody. I will do my best to get the grading done by Friday at noon, and then you guys will be able to see what that is.
Are we still on the same finals week schedule?
Yeah.
That we were
So.
okay.
Yeah, I think all that's going to be the same. Yeah.
Okay.
Okay. Okay. See you later. Have a great weekend.